Today we are going to take a look at the heart muscle itself and what makes it different than other tissues. For comparison, we should review a simplified version of the action potential of a nerve cell. You've learned about a membrane potential in its resting state dominated by the potassium ion, and it's around -70 millivolts. As EPSPs stimulate the dendrites, an adequate stimulus or threshold is reached, triggering the opening of voltage-gated sodium channels. This leads to an influx of sodium ions and the cell's depolarization. Repolarization occurs via the opening of potassium channels. The myocardium is interesting. Just like skeletal muscle, it requires calcium and has actin and myosin complexes. The myocardial action potential is not initiated by a nervous stimulus, though it is regulated by one. Myocardial cells during phase 4 are hyperpolarized and dominated by the potassium ion. When the myocardial cells are activated, their depolarization, or phase 0, is modulated by sodium ion influx. Phase 1 follows with the sodium gate inactivation and the initial repolarization via potassium channels. But phase 2 is what makes cardiac myocytes unique. This is when the calcium channels open to balance out the potassium ion efflux. This is the plateau phase and is vital to prolonging the action potential. You will also find that calcium is going to be important for regulating the force of contraction and can be manipulated with different drugs. Phase 3 is the repolarization phase, again dominated by the potassium ion's efflux. Be sure to pay close attention to the difference between these cells, cardiac nodal cells, nerve cells, and skeletal muscle. There is a phrase that's used when talking about heart muscle. It is calcium-induced calcium release. This phenomenon is unique to cardiac myocytes. These contractions, which are coupled via gap junctions, coordinate their movements. When an action potential from a neighboring cell triggers the depolarization of a nearby myocyte, the voltage-gated calcium channels open up and the calcium rushes in. Then it binds to the ryanodine receptor on the sarcoplasmic reticulum, which causes a surge in intracellular calcium. This calcium binds to troponin to initiate contraction. Calcium is then actively taken up by the sarcoplasmic reticulum and is pumped out via a sodium exchanger, which had its gradient established by the sodium-potassium ATPase pump. This mechanism and the cycling of calcium will be a key regulator of cardiac function. It is acted upon via physiologic mechanisms to increase the contractility during beta-adrenergic stimulation and manipulated by drugs like digoxin. These will be further explored in class, but beforehand, think about what would happen in states where the calcium was low. What would happen to muscle cells if they were placed in a high potassium environment and the resting membrane potential of the heart was disturbed? Again, thank you for watching and good luck with your studies.